this series of lectures is to introduce, so to give a gentle introduction to formal verification of multi-agent systems, at least in the sense how I understand it, or in the sense of what I have been doing in my research for the last, let's say, 15, 20 years. So the idea is that we want to talk about multi-agent systems in a meaningful and precise way, and possibly use it to provide methodology for specification and verification of some interesting properties. I will start with why. So the first part of this lecture will try to convince you that the problem is relevant and somehow useful. Then I will show you some. I will give you some idea about what kind of multi-agent systems I'm talking about, and then I will move on to an introduction to some logical languages that can be used for specification. And that's the idea of this lecture. And I hope, if I'm not too slow, because normally, I mean, I'm notoriously too slow and take too much time in delivering the topic. So I hope to give you a glimpse of an actual verification tool that can be used to verify some simple properties in some simple models of agent systems. I believe you have access to the slides for the lecture today, and the idea is that before every lecture, like at least one day before the next lecture, I will give access to the lecture slides again, so that you can have a look beforehand, or you can make notes on it. And in terms of other reading materials, you may, if you are interested in a more detailed and in-depth treatment of the topic, you can have a look at those books. So basically, the first one is a monograph I published a couple of years ago, and it's, in a way, it's a counterpart of this course. So this course is meant as like basically a shallow presentation of very deep topics. So I'm not going to go very much into mathematical definitions. I will show no proofs, maybe mention some theorems, but not too often. The formal stuff is in the book if you want to check it. And okay, it's like a breach of modesty, but I want to say that the book has already been used by some of my colleagues as a script, as a lecture script. I think at least at the university in Bergen in Norway, Utrecht in the Netherlands, Naples in Italy, and Luxembourg as well. So and they found it, and moreover, not only the lecturers found it useful, but also the students, which is always the most important test. And if you want an even deeper exposition, the book by Shoham and Leighton Brown is an introduction to formal models of multi-agent systems. And if you want to know more about the formal verification and especially model checking, the books by Clark and Bayer and colleagues are good introductions. Okay, so the slides, some parts of my slides are based on slides that are prepared with other people. This is the outline of the series. So today I'm going to. Today we are having introduction to introduction. Basically, I'm going to introduce the basic ideas, and then I'm going to move on to the simplest modal logics that can be used for reasoning about multi-agent interaction, namely temporal logic and epistemic logic, so the logic of time, that allows us to talk about the dynamics of a system or some features of the dynamics, and the logic of knowledge, which allows us to talk about some properties of information flow and knowledge and beliefs of the interacting agents. Then I think the next lecture is 3 weeks from now. I'm going to move on to more sophisticated properties that talk about strategic abilities. So what agents and group of agents can enforce or make sure about if they choose the right strategies. And then I will present how to specify properties like that, and also the first attempt to define verification algorithms. Then in January, I think, I will talk a little bit about practical aspects of model checking. Okay, practical from a theorist point of view. Okay, but at least we will take into account some concerns about how these, fantastic algorithms with fantastic theoretical complexity results from the second lecture, how they work in practice. Hopefully, they work awfully, and what can we do about it, possibly to somehow overcome the complexity barrier. And then a part of the, let's say, toolbox for limiting the practical complexity of verification is model reductions, which is the topic of lecture 4. And then during the last lecture, I will give you a glimpse of even more sophisticated logics and properties that can be addressed when verifying multi-agent systems. Okay, so this is the outline of the lecture today. Let's move on. So I promised motivation, or I promised the why part. So why formal specification and formal verification? Well, okay, the idea is to use a formal language to specify properties that we are interested in. So typically, there is a short or usually a long list of properties that one would like to have satisfied for a system that we are designing. So let's say we are designing a satellite communication and coordination protocol, and it should, let's say, satisfy properties like whenever a satellite tries to coordinate with another satellite, the other satellite responds in a finite time. That does never, if we want some kind of information security, that's we may want to require that some sensitive information will never leak, or if it leaks, only a small amount of information, of sensitive information, leaks to third parties, and so on and so on. And my experience is that it's very nice to talk about that, like when we are brainstorming about design, and everybody agrees, like we are sitting around the table and trying to come up with a list of desiderata. Everybody agrees that these are very, very important and intuitive properties. But then, much later into the design or even implementation phase, we are very likely to discover that everybody in the room understood the let's say, plain text specifications in a completely different way, or a slightly different way. And I remember I heard a talk by a guy from Tata Consultancy. So it's a part of basically it includes the software engineering part of the Tata, the Indian Tata conglomerate. And he said that according to the data collected by their engineers, 90% of errors really have their sources at the specification phase, or basically the system requirement specification phase, and 90% of errors are detected at the implementation and testing phase, which means it's very costly. because basically if you detect something so late in the system development pipeline, you have to go back and redesign the system and then redo the detailed design, the prototyping, the implementation, and so on. Or you have to accept that the system will be buggy. Yeah. So the idea here is we may want to use some formal language which has a precise semantics already at the specification phase and the prototyping phase and do some verification at the prototyping phase to make sure that we are on the right track. And this is what this part says, that well, if we do formal specification, it typically helps to disambiguate the requirements. So to make sure that we are really after the same requirement, all of us, that stated in English or in Polish or Indian for that matter. Then while we are disambiguating the requirements, we typically realize that each of us has a number of implicit kind of subconscious assumptions about how these things should be modeled and reasoned about. And quite often these assumptions differ. So making them explicit helps a lot. And then, so that was the specification part, which is already very, very useful. Maybe even more useful than formal verification. But then, on top of that, we can try to do some formal reasoning in order to prove that the requirements hold. So let's say we already so we move on from requirement specification to architectural design, or we move further on to prototyping. We can try to use some nice techniques to prove that the requirements hold for the prototype or for the design. Of course, with respect to the assumptions, implicit and explicit assumptions that we are making. And another possibility is, while doing the verification, we may actually discover that the requirements are not satisfied for the design that we are thinking of. And the nice feature of formal verification techniques for temporal and strategic logics is that very often, if the answer is no, the property does not hold, the answer comes with a counterexample. So it shows some kind of, let's say, execution path, for an example, that invalidates the requirement, which is a very useful information because it can be used for debugging. Okay. And then, since I will talk a lot about strategic ability, not so much today, but from the next lecture on. Okay, so for today, I'm going to focus on temporal logic, and the motivation for temporal logic is first and foremost, it was used and it can be used for specifying standard requirements like reachability, safety, fairness, responsiveness, and so on. And they can be specified in a very neat way. And let's say the more usual the requirement type, the simplest verification procedure can be used. For strategic ability, this is my motivation why reasoning about agent strategies matters is in a system where we talk about autonomous agents that can make autonomous decisions, make and execute autonomous decisions. Most properties that we are interested in really refer not to what happens if the agents act in a dumb way, but rather what happens if they act smartly, right? So do they have a way, let's say, if we are talking about a voting procedure, a design for an election, we don't want to ask, okay, what happens if the voters act in a completely stupid? Or maybe sometimes we do, but in most cases we want to ask, okay, is there a recipe for the voter so that eventually he or she is sure that their vote has been cast and recorded and tallied in the correct way? Okay. Do the election officials have a recipe for behavior so that at the end the election is concluded and approved by the electoral by the state, the national electoral commission, and so on and so on? Okay, so this is, let's say, kind of functionality requirement. We are asking, is this functionality available to this agent or a group of agents? And then security, very often, not always, but very often, is kind of the dual of that. So it's not about, so the functionality is about the ability of the legitimate users to accomplish their legitimate tasks. Security is often about the inability of the bad guys to do bad things to the system. Again, this asks about, do they have a smart plan? Do they have a strategy to compromise the system? So strategic ability. And I will show you in the next lecture, I will show you the first logic, ATL, alternating time temporal logic, how it can be used to specify such properties. Strategy logic is much more sophisticated, and I hope to convince you during the last lecture that it also provides interesting specifications. And as I said, we can try to verify such specifications by means of model checking. Okay, so as a motivating scenario, I typically either use a voting scenario or rescue robots. So let's use the voting scenario for this series of lectures. The idea is that we have a voting situation, let's say a presidential election. There is a number of voters, but there are also, and let's say, let's assume that we are talking about just traditional voting, paper-based voting at polling stations. So each of the voters is supposed to get to a polling station, enter the voting, well, first register for the vote, then enter a voting booth, select one of the candidates from the ballot, and then then cast the vote and exit the polling station. Okay, so this is one possible scenario. Another possible scenario is postal voting. Register for the vote for voting by mail. Wait for the election package, then unpack the election package, sign the declaration, fill in the ballot, put everything in the right envelopes, and send it by mail. And I think most people here do not realize that we actually had postal voting in a presidential election once, and it was the COVID presidential election. So there was a lot of hassle about the procedure. At the end, it was done in a very limited scope, so only for expats, for Polish people living abroad, and I think there were 2 communes in Poland which were in like heavy lockdown, and postal voting was used there as well. So since I lived in Luxembourg at the time, I did participate in the procedure. It was very badly designed, by the way. So it was lucky that it was not used nationwide, because it would have been a disaster. It was very easy to manipulate that, like stealing votes and impersonating another voter and so on. So just as a story in particular, I could, if I want, at that time, I think it was me and my wife, and 3 of our kids were already adults. So any of us, the fastest one, could grab the envelopes, the election packages from the mailbox, fill in for the others. Okay, fake the signature. I mean, at the Electoral Commission who counted the votes, nobody really compared the signatures to anything. And the only authentication, so, okay, in a way, it was two-factor authentication. The first factor was signature, and the other one was social security number, the PESEL number. And of course, we know each other's PESEL numbers. So the quickest one, takes all basically. And if I was quick and unscrupulous, I could have had 5 votes instead of 1 in the election. So. And this is basically like a motivation for the second part of the second paragraph. So there can be bad guys who want to steal votes, bribe voters, blackmail them, basically coerce them to vote for a different candidate than the voter really likes. And this can be just ordinary people, but most typically they would be like representatives of a political party, or maybe representatives of another country, another state. Because why do a costly war if you can just install your representatives as the leaders of the country, and then you don't have to do anything more. Okay, so this is the motivating story. And maybe one more thing about the voting motivation. This is actually also our main application domain where we test the ideas. And this started some years ago, maybe 10 years ago, when I joined an information security research group in Luxembourg of Peter Ryan. And they do a lot of secure voting protocols. And I got interested in them. And my idea was that typically what they focus on is the crypto part and proving that the crypto works correctly. But the multi-agent perspective is more about the people and their interaction and what can go wrong or what can be improved when we take into account humans, their preferences, incentives, and so on, humans participating in the voting procedure. Okay. So, how to model a distributed system? Because an agent system is a specific kind of. By the way, I think I haven't said that at the beginning. If you have questions, just interrupt. Okay. So don't wait until the end of the lecture. So, how to model a distributed system? There's a very powerful idea in computer science. Use a transition graph. If you think of, I don't know, block diagrams, control flow diagrams, data flow diagrams, and so on and so on. These are basically, all of them are some kind of flavors of transition systems where the nodes correspond to the states of the system or situations, let's say, in a more general term, and the edges correspond to transitions or changes of state. And a multi-agent system is just, let's say, a distributed system where the components, we assume that they can make autonomous decisions and they can act in a purposeful way. Okay, so a very simple example. Let's say we want to model the interaction of 2 robots. There is a carriage on a circular track. There are 2 robots on the opposite sides of the carriage. Each of them can push or do nothing. If they both do nothing, nothing changes. If they both push, we assume they push with the same force, so nothing changes as well. If one pushes, the other one waits, then the carriage is moving either clockwise or anti-clockwise. Okay, and in order to make the model of the scenario discrete, because I'm only going to talk about discrete state systems and actually finite state systems, let's identify 3 different positions of the carriage that we are interested in, and on top of that, we assume that there is this is not only a discrete distributed system, but a synchronous distributed system. So there is a global clock ticking behind somewhere, and with every tick of the clock, every agent decides what they want to do, and the transition happens accordingly. Okay? So the simplest model of what can happen is like this, and well, anything can happen basically, right? So this is a fully connected graph, because depending on what the agents want to do, for every given position of the carriage, we can move to any other given position of the carriage in one step. What if we want to, I said these are agents. Each of them has 2 actions available to choose at any moment. So, and I said that the decisions and their execution happens synchronously. So if we want to somehow represent it in the model, we will label the edges by tuples of actions, 1 per each agent, with the idea that, okay, if the system is in Q0 and they both decide to wait, then the system stays in the same state. So the transition occurs in a loop. If they both push the same, if the first one pushes, the second one waits, the system moves from Q0 to Q1 and so on. Okay? So, yet another dimension or yet another layer of concern. We might want to reason about information and knowledge. So let's assume that the first robot has some kind of, let's say, a camera that allows it to distinguish between distinguish the color of the surface. So for this robot, these 2 situations will look the same, but let's say those 2 will look differently. And the second robot has some kind of, I don't know, some kind of sensor that detects the surface, the texture of the surface. So it will be able to distinguish between rough surface and smooth surface. But let's say these 2 situations will look the same for the robot. Okay? So this is typically modeled by epistemic equivalence relations. So basically equivalence relations that partition the state space, and they connect states that look the same according to the information that the agent has. Okay? So it says that Q0 and Q2 will be in the same epistemic equivalence class for agent 1, but Q1 will be in another equivalence class. Okay. So that's of course, that's a toy example, but it's quite useful. It will be useful in demonstrating, especially the properties of strategic interaction. Another very simple example, but a bit more, he's touching on real concerns is voting and coercion. So this is, I think that's a painting from like 200 years ago in the UK. And if you look carefully, this guy here, it's a metaphoric depiction of a coercer. So he's standing with a hammer over the voter's head and making sure that the voter casts the vote for the right candidate. So of course this is a metaphor, but in those days, I think I learned not so long ago that the history of secret ballot, that the secret ballot was introduced for the first time in the UK in 1872. So it's like 150 years ago only. And before that, all votes were cast in public and they were publicly available. even after the election. So everybody could go to the municipality office and check how you voted. And the rationale was that, okay, every man at that time should stand by his vote. So should take the responsibility for how he voted. But the side effect was that it was extremely easy to force people to vote if you had a handle on them. Like, I don't know, they were renting, they were working for you or renting a place from you. Then it was very easy to say, okay, you vote for this, you vote for me, by the way, and or the next day you are fired, right? Or buying votes. Basically, buying votes was an industry almost, right? So it was just customary. People were standing in front of the voting places and paying voters extra money for casting the vote in the right way. So it was a serious concern if you have this, ideal that an election, the outcome of the election should be somehow representative for the distribution of preferences in the society. Okay? So how can we model this kind of interaction? And again, in a very, very simple way. Well, it can be a graph like this. So there are two players, the voter and the coercer. At the beginning, the voter can loop with the wait decision for an arbitrary amount of steps. Then at some point, he or she can decide to vote for candidate 1 or for candidate 2. And then the procedure moves on to a different state because, in one state, I have voted for the first candidate. In the other state, I have cast a vote for the second candidate. But this dotted line indicates that these two situations are indistinguishable for the agent called C, for the coercer, right? So the coercer doesn't know which one of them is really the case. He knows at this stage that one of them is the current state, but doesn't know which one. So it's like playing a card game, right? You know what is the set of legal hand distributions, but you can only, if you don't cheat, if you're not cheating, you can only see your own hand and not the hands of the other guys. And there is typically a large number of possibilities that you have to consider. Okay, and then suppose that there is some kind of certificate that some proof of vote that the voter might give to the coercer. And nowadays it's actually easy because the coercer can request the voter to take a picture with a smartphone, a picture of the ballot, and then show the picture after quitting the polling station. And the voter can decide to show the picture, to give the certificate, or not give, refuse to give the certificate, right? Which the difference is that in this case, the indistinguishability link is broken, okay? In this case, the coercer knows precisely where we are, which state of the system we are in, while in this case, the coercer is still uncertain, in particular, is uncertain about the value of the voter's vote. And then the last stage is the coercer can decide to either punish or not punish the voter, and the game ends. Okay, so as I said, the nodes of the graph correspond to states of the system. The arrows correspond to transitions labeled by actions of all the players in the system. The dotted lines, they show indistinguishability of states. So they connect states that look the same to the given agent. And I haven't mentioned this thing is here. These are so-called atomic propositions or propositional variables. These are just labels of states that we might want to use. So kind of basic properties of states that we might want to use in the logical formula that will specify some interesting property. Okay? So for instance, this atomic proposition, it will label all the states where the voter has already voted for candidate 1, This labels all the state where the voter number I. Okay, there's just one voter here, so maybe the I is redundant. Where this voter has already finished the election experience, and so on and so on. Okay, so one of the problems that I will come back, especially during the third lecture, is that it all looks very nice in a very simple example. Okay, so we don't take we basically we abstract away from all, most features of the voting procedure. We just look at the bare bones of the voter-coercer interaction. Okay, does the voter give any information about the value of his or her vote or not? And does the coercer punish the voter or not? Okay, I mean, or dually, does the coercer pay the voter, pay the bribe, or refuses to pay the bribe? That's it. Even for this, we have to face, you probably heard of something called exponential explosion of the state space, or at least exponential explosion. It shows its ugly head, even if even if we abstract away so many features of the interaction. So this is how the graph looks for just one voter and one coercer. If we want to reason about two voters and one coercer, it already looks like this. Okay? And for three voters, the graph already cannot be shown on a slide because it will be just like, you know, a mass of black dots. So so the set of states and the set of transitions grows exponentially, and this is a big problem for from the point of view of verification. But today we mostly look at the specification part, and that is somewhat easier. Okay, so let's start with temporal properties. And to motivate this part, let's say we want to express a number of properties. One of them is kind of reachability, or kind of no, not really liveness, reachability property, and says the voter will eventually cast a vote. Okay? So the voting procedure is constructed in such a way that you know, no matter what happens, I have the opportunity to go and vote, and my vote will have been cast, which is not obvious. I mean, we are used to the idea, but there is a large part of the world where polling stations are not so easily accessible, and sometimes they are not so easily accessible by design. So, so I had a very interesting conversation. I'm also there is a series of conferences called eVote ID, and a very nice community of researchers. And very nice means it's really interdisciplinary. So there are you know, crypto people, formal methods people, just plain computer scientists, but also sociologists, psychologists, people from public administration, and basically they discuss the properties and designs and implementations of voting procedures that would be, you know, would satisfy some basic security and integrity requirements. And for instance, a big concern in Nigeria is that polling and it's a huge country, right? I think it's like 200 million people. So it's like 5 times, more than 5 times the population of Poland. And the problem is that the political sympathies are mostly ethnically aligned. So they correlate very closely with the ethnic background. There are 3 main groups. I think it's Hausa, Yoruba, and Igbo. Typically, Hausa and Yoruba ally to run the government, and Igbo are in with the main opposition party. So since the government has a lot of control over the design and execution of the election procedure, they understaff the polling stations in the provinces inhabited mostly by Ibos. Okay, so the polling stations are too scarce, and there are too few election officers at the polling station, so that it takes a lot of time to get to the polling station because it's not necessarily you have a highway to get there. And then the queue is like 12 hours. Okay? And then, the election, the time window closes, and if you haven't made it, well, sorry, mate. Yeah? So this is how you can easily manipulate the outcome of the election without really, stuffing the ballots or putting a gun to people's heads to force them to vote in a particular way. Putting the gun is more like Kenya. So it is this kind of integrity property. The voter will eventually cast a vote if, in the procedure, we assume that the voter is moving towards that goal, is an important property, and it's not obvious that it is satisfied. Okay? Then some kind of information security property, the voting system will not reveal how a particular voter has voted. And the last one, which I would call kind of voter enfranchisement, which is the voter can choose to vote and can refrain from voting. Or at least the voter might vote and might refrain from voting in a weaker version. Okay, so let's consider these three properties. We want to express them in a more formal way. And a more formal to me means using mathematical logic. And in particular, using modal logics that are typically used and worked upon in multi-agent systems. I took the picture in Oxford. Okay, so this is my picture for showing that the path of logic is not accessible to everybody and not at any time. So, but I hope, I think we are between 7 a.m. and 8:30 p.m., so we should make it. Okay, and I guess unsurprisingly, in order to talk about temporal properties, we will use something called temporal logic. And the idea is that we take propositional mathematical logic. So I hope everybody had some course of mathematical logic somewhere, buried very deep in their past. But the basic idea that we can use some propositional letters for some basic properties, and then we can use conjunction, disjunction, implication, and so on to construct more complicated sentences. And there are truth tables to tell us how to evaluate the truth, whether a conjunction or disjunction is true or false. I think this is, I'm assuming that this is all familiar to you. Now, on top of that, besides operators like and, or, if, then, we add these special funny creatures, these circles, boxes, and so on, with the meaning that, okay, we are going to look at the evolution of the system in time, discrete evolution. So this state, the next state, next, and so on, until, the end of time. And we might want to say that, okay, phi is true now, we will express it by just phi. Okay? Phi is true in the next moment, we use the circle. So maybe now it's not the case, maybe now I haven't cast my vote yet, but in the next moment, the vote will be already cast. Okay? Then the diamond says, yeah?
It calls for the next moment, but does it concern all the other moments?
Not necessarily.
Okay. It could be false.
It could just blink for a moment, okay? So it will, so for example, if we are talking about my vote being cast and registered, it might be that it is cast and registered in the next moment, and then later on somebody, destroys all the ballots. This property is still true, okay? I can come back to the property, the other property later. Okay, so the circle talks about strictly the next moment, one moment from now. If we want to require that phi will become true in some future moment, okay, maybe now, maybe in the next moment, maybe 10, 20 moments from now, then we use the diamond. It's the model operator for eventually or at some future moment. And then the box is about the dual. So in all moments from now on. So phi, it says that phi has to be true now, in the next moment, 2 moments from now, and so on until forever. And the last one, I don't think I'm going to use it much. So phi is true until the moment when psi becomes true. It's mostly interesting from the theoretical point of view, because basically you can use this to express all the others. So when you define the syntax and the semantics in a very formal way, then it's enough to define it for until and use like derivation rules for all the others. But as I said, it's more like, these kinds of theoretical investigations for just basic mathematical logics. How many axioms do you need? And the answer is one axiom is enough, but it looks horrible, okay? So basically from the practical, or even semi-practical point of view, who cares? You always use more natural axiomatic systems. Okay, and why temporal logic, or how did temporal logic emerge? I think it was defined in mid-1970s by logicians and linguists. So the original motivation for temporal logic was the idea that we can use this kind of logic to disambiguate some phenomena related to tense, to grammatical tense in natural language, past tense, future tense, and so on. But then computer scientists realized that some important properties, some important requirements that already had been considered for many years before as essential requirements. Let's say if we want to specify the properties of parallel processes and coordination, communication, things like no deadlock, no starvation, no violation of critical section, and so on, then they can be expressed in a very neat way using those temporal operators. And in particular, to be a bit more abstract, if we want to express safety properties or reachability properties or fairness properties, they correspond to very simple templates of temporal formulas. So let's start with safety. And the typical safety requirement says something bad will never happen or something good will always hold. Okay, so let's say the critical section of the system is never violated. There's never a moment when two different processes are inside the critical section, right? So this is typically specified by means of the box. Usually we want to say that always from now on some specific property must hold, must be true. So maybe a more agent like motivation. If we are planning if you are making a business plan for a small enterprise, maybe a good idea is to specify that I will never go bankrupt, right? So this formula here says it must always be the case that not bankrupt, then that I am not bankrupt. Okay, reachability, something good will eventually happen. Okay, so for instance, if I go to the polling station, I will eventually be allowed to cast my vote. Or in the business scenario, maybe I want to specify that it's well. I'm not only happy that I will never go bankrupt. I need something more. I want to eventually become rich. Yeah.
I'm rich today, but I will be broke tomorrow. Does it also hold?
Very good. This is a better specification. Yeah. Because it can be the case, I mean, this specification is indeed satisfied if, a month from now, I become very rich by robbing a bank, but then one day later I'm caught, or Louvre Museum, by the way, and one day later I'm caught by the police and I'm in prison and I don't have the goods anymore, right? So this is a better specification. It says, okay, there is laughable. Yeah, was job as well. So if you think of the timeline, yeah, so this is the point number 0, and then the first specification is satisfied if there's just one point later on when I'm rich, and then not anymore, right? So the second specification says that there must be a point in the future which satisfies always rich. What does that mean? For all the points from that moment on, rich has to run. Okay? So I become rich at some point and stay rich forever. And then coming back to Martin's question, if you want to specify that phi will become true in the next moment and stay true forever, then you do it by this combination of operators, right? So in the next moment, always phi has to be true. So in the next moment, phi must become true and must stay true forever. Okay? And that's a large part of the appeal of logics like that, because you can combine these operators in a very simple way to account for quite sophisticated properties. And in particular, you can use it to disambiguate what we really mean by some kind of requirement. Okay, so if somebody says that, I don't know, the vote will have been registered, do they really mean that it will have been registered and we don't care what happens afterwards? Or maybe this should be preserved. The trace of the vote in the election system has to be preserved forever, or at least until some point in time. Yeah. So coming back to reachability or achievement requirements, they are typically specified mainly using the sometime in the future operator, but of course possibly in combination with other operators. And then maybe this is not the most important kind of properties for us, but in general it is very important, especially for asynchronous systems, kind of fairness or service requirements. So whenever something is attempted, then it will be successful. Whenever something is requested, some kind of, let's say, whenever a process requests access to a resource, it will be eventually granted the access by the server or the provider. So whenever I need money, I will eventually get the money. Okay? So it says, for all the future moments, if at that moment I need money, then there will be a later moment when I get the money. Okay? So you may notice that a kind of an implication of this is that I will get the money infinitely many times if the time flows ad infinitum. Okay? And usually the fairness or service properties are specified using a combination of always and then eventually. Okay, so this is the formal semantics, but I'm not sure if how are we doing with time? Okay, we still have half an hour. So maybe just to give you a flavor how this is usually defined. So the formal semantics is we want to define the meaning of a formula given a particular model, a particular, let's say, transition graph, like the ones that I showed you on the previous slides. Okay, so this is specified. So this is the satisfaction relation, and it says in a given model M, in a given transition system M, and in case of linear time logic, we also consider a particular execution path, an infinite execution path. So a sequence of states starting from the current state and then moving on along the transitions. And this part is the formula, okay? So if we talk about an atomic proposition, then we just look at whether the current state in the model, so the initial state of the path, is labeled by this atomic proposition. Okay? Conjunction, disjunction, negation are defined in the standard way. So basically, if we are asking, is not phi satisfied in a given model and at the beginning of a given path, then it's basically checking whether phi holds and flipping the answer. And then the temporal operators are basically evaluated by somehow changing the path which is in the context on the left-hand side of the satisfaction relation. Okay, so if we want to evaluate next, we just cut off. So we start indexing the states from 0. So the current state is the state number 0, the next state is number 1, and so on and so on. So basically this says is, if we want to check whether phi is true in the next step, in the next moment, we take the execution path, we clip off the initial state, we take the rest as the new execution path, and then we evaluate phi on it. Okay? Why such a complicated definition? Because if phi includes some further temporal operators, we need a whole infinite path to evaluate it on. Okay? And similarly for sometime, always, and until. And for those of you who have understood what I just explained on the slide, congratulations. If you haven't, don't worry. At least you understand the main intuition, at least, right? Yeah.
That first line with always.
Yes.
Starts from I.
Yeah. So it says for all possible indices starting from 0.
So we have multiple checks though.
Yes. So this is the formal semantics. This is not a procedure for verification, because if you just use it as a recipe for verifying statements, you never end the verification, right? Because indeed it has to check infinitely many cases. But then, so this is very mathematical, and for mathematics, infinity is not a problem, right? But there are much more efficient algorithms that allow you to verify things, checking only finitely many, doing only finitely many checks, and sometimes quite few checks. So indeed, here you need to check whether phi holds on all lambda, and then if it holds on lambda without the initial state, on lambda without the first two states, and so on ad infinitum. Okay, so let's test the intuition on the voting example. So this property says eventually, sometime in the future, we will have vote V1 or vote V2. No. Why? And implicitly, okay, I haven't said one thing, but for a transition system, if we have just a linear time formula, implicitly we mean on all the possible executions. Okay? So this is true if it holds on all the possible infinite paths through the graph. Okay? Now, there is this path here that loops in Q0 forever when neither vote V1 nor vote V2 is reached. So this does not hold on all paths in the graph. Okay? So how about this? For all paths, it is always the case that if we have vote V1, then we don't have vote V2, and we don't even have it in any finite amount of steps. Yes, because, well, it's easy in this graph to check all the paths where we reach a vote for candidate 1 at some point. So it's this half, basically. And in none of the states we have vote V2, even if we move on a little bit further. Okay, so let's come back to the motivating example and try to specify the voting properties. The voter will eventually cast a vote. I think it's quite obvious how it should be specified. We basically need to take this diamond. Eventually, sometime in the future, the vote will have been cast. The only thing is we want to allow for casting the vote on any of the candidates, so we can use the big disjunction, right? So we can say for any possible name of the candidate, there is a candidate name such that the vote will have been cast on that candidate. Okay? The voting system will not reveal how a particular voter has voted. Well, an easy way to specify that is just with the bare safety requirement template. So always not revealed I, but it's not very satisfactory. We would like to, if we want to expose the logical structure of the requirement, we should somehow refer to the knowledge of the other participants, right? So that, no third party will ever know how I voted. And we cannot express it in linear time logic. Why? Because we need some kind of operators for knowledge, some logical means to address knowledge of the other parties. The voter can vote and can refrain from voting. It cannot be expressed in linear temporal logic, because in linear temporal logic, we can only talk about what must happen on all the execution paths, and we need some kind of branching time operators for this, so that there is one course of action where I will have vote and another course of action where I don't vote. This cannot be expressed in LPL, and we are moving on towards that in just a moment. Okay, so as I said, one thing missing. The second missing thing is our ability to distinguish within the logical formula between what must happen and what might happen. So between different possible courses of action. And this is addressed by branching time logics. Okay, any questions? No? Or bad? I don't know. Okay, so let's move on to branching time logic. There's something called CTL, computation tree logic. So we are already moving into like more ugly logic names. And you might recall that linear time logic was created by philosophers, logicians, and linguists. But now we are moving into creatures that have been created by computer scientists. And I think computer scientists are not the best guys marketing-wise. So we tend to name our products in a kind of counterproductive way. So, and computation tree logic is not the worst. So you will see worse in the next lecture. Okay, but the idea is that okay, there's not much about computation actually in the very idea of the logic. The idea is that we model the execution of the system as a branching time tree. So we consider, if we look at the let's say the transition system, we start from the current state. It is the root of the tree. And then we unfold all the possible courses of action into the branches. And if we assume that we only talk about infinite paths or maximal paths, then most of the branches of the paths will be infinite. Some of them might end with a deadlock. Okay. And then a big appeal of CTL is basically that it takes LTL and adds just those two operators, so-called path quantifiers. So before we talk about the temporal pattern that we like, so safety, reachability, and so on, we just say whether it has to hold on all the possible executions of the system, or at least some of them, okay? And this is already very powerful. So, okay, let me skip this vanilla part. Okay, so what we add is, now the reference point is a model, a transition graph, and a state, a node in the transition graph. And if we want to say that some temporal property gamma holds, that there is a path such that gamma holds, it means, okay, there exists an infinite sequence of states in model M starting from Q such that gamma holds on that sequence of states. And dually, for all paths, says that for all the infinite sequences of states starting from Q, we have that gamma indeed holds on that sequence of states. Yeah? Okay, I wanted to skip that for the sake of time. But the difference is that CTL star is really the full language I'm talking about. CTL is a very restricted version. And they are called this way for historical reasons, because I think Emerson and Clark came up first with a very restricted variant. And then some years later, they realized it can be nicely extended. And if we extend it, it's much more logical. It has a much more logical structure. But the restricted thing was already published and recognized, and everybody knew about it. So basically, for the extension, they added the star. They called it CTL star. The reason why people still consider the restricted version as important is that it has much better computational properties. So the big thing, it has very nice expressivity. It allows you to express a lot more than the restricted thing. But at the same time, it requires, it's more demanding if you want to verify anything, or you want to do, I don't know, theorem proving, satisfiability proving, and so on. So if you really want to achieve something like do some verification of an actual scenario, it is typically smart to stick to the less expressive variant, because for those properties, for this limited set of properties, you can design much better verification algorithms. Okay. Yeah. So going back to the formal semantics, for the big thing, which, as I said, has a much nicer logical structure of the definitions, we are adding these two semantic clauses, and then we just benefit from the fact that the rest has already been defined when we provided the formal semantics of linear time statements. Okay, so if you want to evaluate whether there is a path such that gamma holds, well, you need to check if there is a sequence of states starting from Q for which gamma indeed holds. And what does that mean? Well, you have the meaning here, right? So the semantics of LTL is basically embedded in the semantics of branching time logic. Okay, so again, let's have a look at another example. This is something that it's simple rocket scenario, something that the planning community used quite often, let's say 25, 30 years ago. So the idea is that there is a rocket and a piece of cargo, and there are two agents, one with different capabilities. One can load and unload, the other possibly only unload the cargo, and so on. And the question is how to plan their behavior and their coordination so that some particular goal is achieved. So, for example, we may want to make sure that eventually the cargo is in Paris, right? Okay, so basically there are two airports or aerodromes considered, the aerodrome in London and the one in Paris. The cargo might be in either of the places. The rocket can be possibly in the other place. So the challenge was basically, so it was like a toy scenario to test some basic some sanity requirements for a planning algorithm, whether the planning algorithm can handle indeed, that sometimes you have to move the rocket to the other airport in order to pick the cargo. The cargo has to be loaded and then flown, unloaded, and so on. Okay, so let's assume that this is our starting point. So the rocket is in Paris, it has no fuel, and the cargo is in London. And the question is there a path such that eventually the cargo is in the magazine, in the depot in Paris? And the answer is yes. Why? Okay, first we take this transition, which means the rocket is still in Paris, the cargo is still in London, but it has been refueled. Then the rocket flies from Paris to London. Then the cargo is loaded. So the cargo is inside the rocket and the fuel has been refilled again. Then the rocket with the cargo flies to Paris, and then the cargo is unloaded. So the cargo is in Paris, and we are done. Okay, so we have found the path from the initial state that indeed reaches this atomic property saying that the cargo is in the depot in Paris. Okay, for mathematical completeness, we need to have an infinite path, so we can, add any continuation, maybe just the loop here or anything else, but it doesn't matter, right? For the evaluation of this property, only a finite number of steps matters. So this is, I think, an answer to your implicit question that, the formal semantics talks about possibly infinitely many checks, but in fact, for most interesting properties, we always only need to check a finite amount of steps in the transition graph. Okay, more properties. If the rocket is in London, then eventually it will be in Paris. Okay, this is the CTL formalization, right? So it says that for all paths, no, this is not. Okay, let me skip it. Because, I was supposed to show you more properties, but we are running out of time, and I would like to show you the tool in the last, let's say, at least 5 minutes. Okay, so let's come back to the motivating specifications. So the voter can vote and can refrain from voting. This is actually ambiguous, okay? Because we can read it as might, in the sense that there is a possibility that the voter eventually votes, and there is a possibility that the voter does not vote. And this can be specified using CTL, okay? So this is kind of, and you can see that this is a kind of property that cannot be expressed in linear time logic, because it talks about non-determinism. It talks about there is a possible course of action where something happens, and another one where the same thing never happens. Okay, so from the point of view of the starting point of the procedure, we are not completely sure whether this thing is going to happen or not. This is very important, for example, in some security scenarios, because if something can be predicted already at the beginning of the procedure, this is typically a very powerful kind of information about the system for the attacker, which can be and will be exploited. Okay, so this kind of flavor of the requirement can be encoded in CTL. A possibly more refined specification. There is a path such that eventually I have voted, or V has voted for some candidate J, and there is a path such that always none of that is the case. So V never votes for any candidate from the set of given set of candidates. And there is also another interpretation of the statement, which doesn't talk about possibility, but where can means my ability to shape the course of action, enforce a course of action that satisfies some property. And this cannot be expressed in temporal logic. This will be the main motivation for the next lecture, where we consider logic of strategic ability. So if I want to say that the voter is able to vote and able to refrain from voting, you will see how to specify that 3 weeks from now. And then again, nobody will ever know for whom the voter has voted. This cannot be expressed in a CTL or CTL star either, because we need some kind of knowledge, some means for expressing statements about knowledge, which we don't have yet, but we will have them right now. Okay, so and then properties that we may want to express is the coercer does not know how a particular voter has voted. The voter knows how that the coercer does not know. The coercer knows that the voter knows that the coercer does not know, and so on and so on. Okay, so it's I think the biggest fun for epistemic logicians to consider these kinds of complicated nested knowledge and ignorance statements. So let's see how this can be expressed. The idea is very simple. We add knowledge operators. Ki phi is interpreted as I knows that phi. And the semantic is very simple. It's basically you look at all the states that look the same from the point of view according to the information available to agent I, and phi must hold in all of them in order to say that the agent knows that phi. So it's basically like playing a poker game or a bridge game. And okay, I see what I have in my hand. I don't know. I don't have any other information. So basically, if I am to say that I know that the agent on my left has the ace of spades, it must be the case that in all the possible card distributions consistent with what I see, the ace of spades is here. Yeah. Okay. Collective knowledge, I don't think I have the time to talk about that much. There's just to signal that if we want to say something like a bunch of agents collectively know that phi is the case, it is not unambiguous. That there are many different possibilities. Everybody knows means each of them just individually knows that phi is the case. Distributed knowledge means if they pool the information together, if they exchange their information, they could realize that phi is the case. And collective knowledge means each of them knows that phi, and each of them knows that the other guys know that phi, and each of them knows that they know, and so on, again ad infinitum. Okay, so this is the formal semantics. Let's skip it. I have some very nice slides how this is interpreted. Let's also skip it. If you have some more detailed questions about how it works, you can ask me afterwards. You can always email me. We can have a meeting, or I can reply by email. Let's go to formalizing these properties. The coercer does not know how a particular voter has voted, so he doesn't have an effective threat. Well, for each of the candidates, it is not the case that C knows that voter D voted for this candidate. The voter knows that the coercer does not know. We just add the knowledge operator for the voter in front. The coercer knows that the voter knows that the coercer does not know. Okay, we keep adding these knowledge operators. And if we want to have it, ad infinitum, we just move to common knowledge. We say that it is common knowledge among these two agents that the coercer does not know how the voter has voted. Okay, I think I must, maybe I will start with combining knowledge and time at the beginning of my next lecture. So let me skip this. Let's just go through the idea of the model checking problem. So the idea is basically it's like a algorithmic counterpart of the semantic rule. Okay, so as input we have the transition system and possibly a point in the transition system and a formula. And we are supposed to answer this question, the question, does the formula hold in this state of this model? Okay, so this is the logical formulation of the problem. This is the, let's say, computer science formulation. We need to implement a function that takes the graph, a point in the graph, and the logical formula. It does some computing, and at the end it returns yes, if the formula indeed holds in the model, and no otherwise. Yeah? So this is called local model checking. The problem is sometimes called local model checking. And the alternative is called global model checking. It takes just a graph without a given point and the formula and returns the set of states where the formula holds. So it seems much more complicated, but the funny thing is, it's often no harder. And in fact, many algorithms for local model checking, they first do global model checking and then check whether Q is in the set which is returned by the algorithm. Okay, so that's the idea of the decision problem. And now I have 4 minutes to give you a flavor how tools for model checking of temporal logic look like. So let me first start. I'm using UPAL, which is a commercial tool for model checking of a fragment of CTL, of computation tree logic. But one can get a free license for educational purposes. So this is nice. it has many disadvantages, but it has one huge advantage, meaning a graphical user interface. Because most verification tools, they are developed by theoretical computer scientists, and they never bother with trivialities like a GUI. But if you want to verify anything, even a toy example, they tend to become very complicated very, very fast, even the specification. So when we started doing verification experiments with my group, we realized very quickly that we are using, let's say, MCMAS, which has no graphical user interface, and then very quickly we are getting like the spec of the model is becoming like 500 lines of specification, which is essentially a code. It's like a very, very high level programming language. Yeah. And you have 500 lines of code. I mean, you have no clue what's inside. I mean, you know what you wanted to put there, but whether it's, I mean, you can rest assured that probably there are some bugs. So if you cannot kind of visually scrutinize that, and there's no simulation functionality either, you are verifying something, but you don't know what you are verifying. Yeah? So it's not extremely satisfactory, let's say. And I think for the Zoom meeting, I need to change the window for the UPL window. Okay, so let's see how. Okay, I think we have a. Okay, so this is some. Yeah. So this is a part of research path that I have done with my colleagues in Luxembourg when we tried to model some basic features of the postal voting procedure for the Polish presidential election in 2020. And it's just to give you a glimpse of how these specifications look. Okay, so obviously, we don't want to specify a system consisting of, let's say, 10, 20 agents by just one monolithic graph. So the idea is that we specify the behavior of every component of every agent with a separate graph. The nice feature of UPAL is that if you have agents of the same structure, like many voters, you want to verify the behavior of 5 voters that basically follow the same kind of behavior, you just specify one template, one graph for a voter behavior, and then you declare how many voters. So in this case, it's 2 voters. 2 instances of the template will be featured in the verification. And then for other components, I think in this case we take 2 electoral commissions, 1 municipality office. There are 2 candidates and 2 envelopes. Okay, we can simulate that. So you can see that indeed there are 2 electoral commissions, 2 municipality office, and 2 voters. No, sorry, 1 municipality office. And okay, something happens, right? So this is a very nice feature. And then we can also verify some properties. Okay, where are the queries? Stop voting. Oops. I lost. No, because I want to import the queries. Okay, so there is another file with some queries. So for instance, this property says that the number of received ballot packages is never greater than the number of sent election packages. So basically, there is no ballot stuffing, right? So It's not that we sent out 10 voters registered for postal voting. We sent out 10 election packages, but we get 20 ballots, and then we are supposed to tally those 20 ballots. So let's check. The verification is running. You can see that it's taking some time, despite the fact that UPAL has quite some optimizations in it. And then again, I will talk about it when I address practical abstraction issues. The main problem, first and foremost, is the state space and transition space explosion. Because if you combine, in our case, I think we combine 7 components. Basically, the state space is the number of local states of each of them to the power of 7. So that's already a lot. So maybe we cannot verify this. Let's stop it. We would need more time, but maybe at least we can verify that there is a path such that eventually this is the case, and this runs much faster. So we get that the property is satisfied. Okay. Intuitively, checking that something is reachable on at least one path runs much faster than making sure that it has to always be the case on all of the paths, right? So I think we reached the time when I need to finish the lecture. 3 weeks from now, I will basically talk about strategic abilities, but I think I will start with a quick recap of temporal model checking, maybe show some more models and verification instances, and address the combination of knowledge and time, and then move on to strategic abilities. Thank you very much.
Thank you for your talk, and thank you for all people who asked questions during the lecture, but maybe, still there are some questions left for this moment, so please ask.
Can you repeat?
Yes, I would like to encourage people to ask maybe some questions.
Okay.
Yeah. So there were a lot of questions during the lecture, and it was very nice, but maybe still someone waits with
just a simple question. How complex problems are you able to handle with this technique?
Okay, so we are aiming to solve very complex problems, but we have been trying for many years, and we are very far away from that goal. So for the moment, we have to abstract away a lot of features that are relevant. I will talk about state abstraction and approximate model checking. With that, we can verify slightly more complicated designs, but only slightly.
Can you try to compare the ability of this technique of formal verification with what we can do with large language models? They will break at some point, but the question is, how far can you go? Because this is something that people now prefer because it's so easy, right? So just put the description of the problem into LLMs and hope that they are going to answer some questions. So, but obviously there are some limitations, and it's very interesting to know what will be their limitations.
Mm-hmm. Yeah. So I will repeat the question for the sake of the people in the audience here. So can I compare the capabilities? So what we can achieve with formal verification versus what people can achieve with large language models, because they obviously have some limitations, but they can go quite far when answering a question. I think the comparison is let's say the functionality, in the sense that what we want to get with formal verification is some kind of guarantees. Whether with LLMs, at least for the moment, you have no guarantees, right? I mean, you are almost guaranteed that at some point they will hallucinate. Yeah. So this is the difference. And obviously so basically machine learning based techniques, they provide fantastic heuristics to answer questions much faster, and often by that token often much better than formal methods. But you use them only in cases when you don't need any formal guarantees.
Well, it will be very, very interesting to see how far you can go with LLMs. I quite agree that you're guaranteed that they will fail at some point. But the question is it worth at all to ask questions of this sort to this kind of systems, and which systems? I haven't looked at the literature, but maybe someone has compared that, which, well, will just warn people when they should not really try because it's hopeless, or whether, well, there is some chance that this will give you an interesting solution also. Well, anyway, that's just a remark. Thank you.
Yeah, thanks for the comment. So, okay, so if there are no more questions, thanks again for coming. Thanks for asking questions during the lecture, and I think we can finish. So, thanks a lot.
Thank you.
Thank you.